All right, so let's go ahead and get started here. We are moving on to a new section. Now, before we do a lot of anything else, I know I gave you a paper. The first thing is not going to follow along with the paper. I want to talk about these numbers. Now, I'm going to rewrite them on here just so that when I post for all people that are out, they can also see it. So I might write some stuff on the board twice. As well as what I'm writing here, just so it all gets recorded. But for these numbers, anybody know what these numbers are that are over here on the sideboard?
149. Oh,
What are they? The 1, 4, 9, 16, 25, 36, 49, 64, 81, 100. You may have learned them a long time ago. You may have learned them more recently. Probably depends. Okay, prime numbers, that not quite. That prime numbers are when you have a number that only factors are one in itself. These have factors that you have two of the same. Right? So 1 is 1 times 1. 4 is 2 times 2. So what do we call those numbers? So if you have 1 times 1 gives you 1, 2 times 2 gives you 4, 3 times 3 gives us 9, and 16 gives us 4 times 4. What do we call it when we multiply a number by itself? There. What are You're getting closer. Getting closer. You said square roots. These aren't square roots. If I square root these, I get a value. Like square root of this one is 1. Square root of this one is 2. Square root of this one is 3. What's the opposite of square root? Squares. These are what you call perfect squares. All right. So why am I writing these out? So again, 1 squared is 1, 2 squared is 4, 3 squared is 9, 16 squared is, 4 squared is 16, 5 squared is 25, 6 squared is 36, 7 squared is 49, 8 squared is 64, 9 squared is 81, and then 10 squared is 100. Then I wrote 2 lines out on the sideboard there. I'm going to write them down here just so, again, they get recorded. Now, these numbers are perfect squares, and we're going to use these in this next section because we are dealing with square roots. And if you know your perfect squares, it'll help you with your square roots. We like to get what's called exact value, which means we want answers that are not rounded. And when you are writing answers that aren't rounded, you're going to do what's called simplifying a radical. So let's look at simplifying a radical on the board here. So we have, let's see. Starting square root of 4. What's the square root of 4? 2, right? That's a perfect square. We know that if we take the square root of 4, it's going to be 2. Right. Next one. Square root of 20. Square root of 20. Another square root of 20. This is going to give us a whole number. Will the square root of 20 give us a whole number?
no.
No, because there's no perfect square, right? That's not a perfect square. You have 16 and then you have 25. Those are the 2 closest perfect squares. So we can't get an exact value by taking the square root and trying to write it as a decimal. That doesn't work. We're not rounding it. So we need to simplify this radical. When we go to simplify this radical, there are a couple options. The easiest option is if we know all of our perfect squares that we have ran out on the board, what is the biggest factor that goes into 20? That's a perfect square. So it has to be something less than 20, right? So we're pretty limited. It's either 1, 4, 9, or 16. 16 going to 20, 9, 4 is the biggest perfect square. So we can split this into the square root of 4 and the square root of 5. What's the square root of 4? 2. So we get 2 square root of 5. And that'd be our answer. All right. So again, if it's a perfect square, we get a whole number, great. If it's not a perfect square, then a lot of times we're just gonna get some type of simplified radical. Now, what if I give you something like square root of 10? Is there a perfect square that goes into 10? Any of these numbers that are less than 10 go into 10.
No.
One does, but that's not gonna help us simplify it at all. So that's it. If we want an exact value, we can't reduce that one at all. We can't simplify that one because there's no other perfect squares going into it. So that one's just gonna stay radical 10. Now, we could have bigger ones like say square root of 90. What goes into 90? All right, 9 is a perfect square. So that's square root of 9 and square root of 10. Square root of 9 gives us 3. We get 3 radical 10. And that would be our answer. All right. So again, this last one, right? We couldn't simplify the square root of 10. Here we have 3 square root of 10. That one can't be simplified at all. So that's it. That's where we stop. That's our final answer. All right. I'm going to do square root of 90 again. I'm going to do it slightly different. So there's actually 2 different ways that we normally talk about simplifying radicals. When we simplify radicals, the first option that I did for these first 4 examples was using our perfect squares. They're up there at the top. Now, maybe you forget what your perfect squares are. All right. Again, it'll help you a lot in this section and from this point on if you know your perfect squares. So if you don't know them, try to memorize some of those perfect squares at the top, at least the first 10. Try to memorize the first 20. But if you do forget, there's another way to go about this. And that's to actually break this down into all of its factors that are greater than 1. All right. So for example, 90. Give me something else besides 9 and 10 that goes into 9. Any other value that goes into 90 except for 9 and 10. Don't want 9, 10, and don't want that. 90. All right, 30 and 3. That's a good place to start. All right, 30 we can break down further. All right. What was it? 15. All right. So 15 and 2. 15 breaks down into what values? 5 and 3. All right, so here, whenever we are doing this method, which is called a factor tree, we now have these broken down into the smallest factors other than 1, right? So going out to 1 is not going to help us at all. We got 2, 5, 3, and 3. If we're doing a square root, we need to look for pairs. So do we have a pair of any numbers on the end? Yeah, we have 2 3s, right? We have a 3 here and a 3 down here. We have a pair of 3s. If we have a pair, all right, so I have a pair of 3s. That can come out. So the 3 comes out. These other values go back under. Now, since they had to go back under, I got to multiply them back together. So 2 times 5 is 10. Same thing would also be true if I had more than 1 pair. So let's say I had 2 different pairs. Well, then I put both pairs on the outside. I'd have to multiply those pairs on the outside as well. All right. So anytime I have a pair, that number comes out. Anytime I don't have a pair, that number stays underneath. Good there so far? All right. Now, we'll do more with this on Monday because we are going to have to do a lot of simplifying with radicals in this next section. There is, when it comes time for the FSA at the end of the year, there's calculator and there's non-calculator sections. You will have to simplify radicals on the non-calculated section. So again, it is good to know those values. Now, we're gonna move on. to Something else. Let me change my screen here. So now. Oh, that is not the right page. That's not the right page. Here we go. Okay. So first page that you guys got, the one that looks like this, again, there's 4 actual pages there. So we're on page 5. All right. Yes. You can get one. Anybody else not get one before we move on? All right, so let's keep going here. Geometric mean. Now, we started talking about geometric mean a little bit at the beginning of last section, because in our green book, we had you define some terms. Geometric mean was one of them, and it explained it with values, kind of like what it's doing at the top of this paper. We have A over X and X over B, and it said that this is a mean, this is a mean, this is extreme, this is an extreme, all right? And it gave some crazy explanation of how to find a geometric mean. You guys remember that? No? All right, fine. Don't worry about it. Throw that out. You're using proportions to set that up. All right, and that's where the name comes from when we're talking about a geometric mean, because we're using proportions and we're doing something with these two means here. But there's a much easier way to think about geometric mean. Geometric mean essentially is if we take two values, we multiply them together and take the square root, you're finding a geometric mean. All this does is cross multiply, you get two x values multiplied together, so you get squared and have square root something. It makes it sound really complicated when it's not. All you're doing is take two numbers, multiply them, and taking square root. So when you see geometric mean, you're multiplying and taking square root. And the two examples, notice 12 times 3, we have 12 and 3. They ask for geometric mean. So 12 times 3, and then take a square root. Simplifies down to 6. On this one, 8 times 4, multiply, take the square root. This one simplifies down to 4 radical 2. Again, they're not always going to give you whole numbers. A lot of times you're going to have to leave them as exact values. But let's do a couple down here at the bottom together. So like 4 times 4. All right. So if we're finding geometric mean of 4 and 4, we need the square root of 4 times 4. 4 times 4 is what? 16. Yeah, that's all right. So multiply, got 16. 16, square root of that is 4. Now, over here, we got, actually, what's that yet? Let's get rid of that. Different settings on the board than I normally do. Maybe different settings. All right, try that. 4 times 6. Now, I can multiply. I'm going to get a number that's 24. And is 24 a perfect square? No. So I'm going to have to break it down again. Well, guess what? I was actually at a better starting point right here because I already had a perfect square, which is 4, and 6, which wasn't. So I could go from that point and just break this down to square root of 4, square root of 6. What's the square root of 4? 2. So my answer is 2 radical 6. And sometimes it's better just to take the square root right away. But it's the same thing for every one of these, right? On this one, you have 6 and 9. Well, guess what? I got that perfect square already. There's no point in multiplying those together. What's the square root of 9? 3. So that's 3 radical 6. On the next one, I got 1/2 and 2. Still no different. I can say 1/2 times 2. What's 1/2 of 2? 1. What's the square root of 1? 1. Yeah, that's what we're doing for each one of those. Multiplying and then square root. So algebraic mean, if you go back to when you talk about means in algebra, that is adding numbers and dividing by how many there are. Same thing as an average. Geometric mean, that's where we're multiplying and taking square root. So every single one of these, that's what you're doing. Now, this still goes along with the idea of proportions, right? I started to show you how there's this idea of means and extremes, and I crossed it all off. But there is a reason behind why we're doing this, right? And it's because we have proportions that work. For the next page, just gonna need that before I let's do this. I don't want to write it. I'm going to write this twice so that they have it at home as well. I'm going to throw my PowerPoint slides back up here real quick so that we can have it saved at home. Give me a second. All right. And now, I'm going to have you add stuff to that same paper. All right. So, you have that diagram up there in the corner. That's the diagram I'm using, but you may want to make it bigger or even right down here in the blank space. I'm going to do a couple things with that diagram. So this is on page 6. You have a diagram that looks like this. It's a right triangle where the right angle is at the top. And then they have drawn in an altitude. They have this labeled as A, B, C, and D. Right? Now, they tell us in the information at the top, when you have a right triangle, and you have an altitude drawn in to that right angle, something special happens. This triangle now has 3 similar triangles. All right. So anytime you have a right triangle, ladies, you listen. Anytime you have a right triangle and you draw in the altitude from the right angle, it splits it into 3 similar triangles. All right. And we know that they're similar because in each one of these, we can clearly tell that there is a right angle and one angle that they share in common. So if you have 2 angles, it's the same, we have to have similar triangles. Now, looking at it, sometimes it gets confusing as to how they match up. So an easy way to separate how to match these up, let's say, now I know they have a statement there already, pay no attention to that for right now. I'm going to change the order. Let's say I do B, C, A. And I want to know what triangle is similar to BCA. By just looking at this, because I know there's 3 of them, is it easy to tell how to match up triangle BCA to the other 2 triangles that are there? For some of you, it might be. For some of you, it probably isn't. All right. Just looking at that, especially the closer in measure A and C get, the harder it is to tell. So, an easy way to do this is to mark the corners. So I'm gonna mark them with just dots for right now. Smallest angle, I'm gonna put one dot. Smallest angle of this triangle, I got one dot. Smallest angle of this triangle, I'm putting one dot. Then for the medium sized angle and the two triangles, I'm gonna put two dots. And then the right angles, I'm gonna put three dots. So look, even in the big triangle, I now have three dots in that corner for B. So matching this up, what order did I go in with these dots? Well, B is the right angle that has three, C has one, and A has two. So that can help me match them up for the other triangles. So if I look at the very small triangle here on this end, I'm going to order 3, 1, 2. So 3, 1, 2, D, B, A. Then I move on to the next triangle. So the medium sized triangle. All right, again, same order. 3, 1, 2, 3, 1, 2, D, C, B. That's an easy way to help match them up. Now, one more thing that I'm going to draw here. That's very, very important. And again, you can draw it somewhere on the bottom. I'm going to redraw my triangle without these measurements. It's a little bit different. So in this triangle, I have some different parts. This part that's drawn in, we know is the altitude. The parts that are coming off the right angle here, these are legs. So this is going to be leg 1, leg 2. This entire side, and I'm doing this bracket for a reason because I'm going to label these individually. This entire side, all the way across, is our hypotenuse. It's the whole hypotenuse. And then that hypotenuse is broken up into two parts, though, because that altitude comes down and it splits the altitude into, I'm going to label as part 1 and part 2. Now, two equations. First, there's an equation to help us find altitude. Second, there's an equation to help us find a leg. They both deal with geometric mean. Right. So the altitude here is found by doing the geometric mean of part 1 and part 2. The leg, each one of the legs, can be found by doing the geometric mean of the adjacent part. I'll explain that in a second. The adjacent part times the whole. So both deal with the hypotenuse. Now, what do I mean by adjacent part? Well, leg 1, all right, is here. Adjacent means what? What is the word adjacent actually? Not together, but so they're adjacent to each other. You said it, next to. So adjacent means next to. So here, leg 1, part 1 is adjacent to leg 1. Part 2 is adjacent to leg 2. So if I was solving for leg 1, I'd use part 1. If I was solving for leg 2, I'd use part 2. Now, I'm going to rewrite that on the board over here just so we have it to look back at. But take a minute to finish copying that. Again, that bottom part is going to be the most important thing. So I'm going to redraw it right here. So, any questions before we move on? Okay, well, all right, I recopied this piece down here, right there, all right, so if you still need the bottom part, it's right there on the sideboard. Okay. All right, good, all right, I'm gonna change this back to the worksheet. Now we're gonna use that worksheet again. All right. So we have our same thing here. This is a little bit confusing what they're actually doing on example 1 and 2. So I'm not using example 1 and 2. I want to be down here to where they have the exercises, and we're going to use some of these examples. So on the first one, all right, great. I have find x. All right, I just have one variable to solve for. Now, there's two different ways you can approach this. And I'll show you why I like these formulas rather than doing the whole mean and extreme, setting up the proportions. But for the first problem, we're going to start by setting up the proportions. We have three similar triangles there. Does everybody see the three triangles? All right, so we've got a small one, a medium-sized one, and a big one. So since they're all similar, we should be able to set up proportions. So on number one, so we should be able to set up a proportion. What proportion can I set up for number one? How many of you guys agree? You do? Think it's good? So let's see, we had three. I'm gonna guess we did this because we have three on the bottom and the next up here, one here, and the next up there. It looks like it should work, but it doesn't. That's wrong. All right. But that's okay. All right. The whole point of me having tried to set this proportion is to show you it's kind of challenging to set it up. Now, the next thing I'm going to do to help you out, let's break it up. We got those two triangles. I'm just going to draw right next to this the same two triangles, but split apart. So now I have 1 and x, x, and 3. So look at those two triangles now. All right. So this was wrong. All right. 3 over 1. X over x. No, still not right. But again, that's okay. The whole point of this is to show you this is challenging. We have the long side of this one. So let's do 3 from the big triangle. And the long side of this triangle is x. Then we have from the big triangle, the short leg is x. And the short leg on this one is 1. That would be a correct proportion. And it's using the idea of the means and extremes, which we can now have a correct proportion. It took us 3 tries, but we have one. We can now cross multiply and solve. Cross multiplying this, we have 3 times 1 equals x times x. 3 times 1 is 3. X times x is x squared. How do we get rid of the square? Square root. Right? Square root is the opposite of squaring something. So we take the square root, that cancels that off. So we now have square root of 3 equals x. And it took us 3 tries, but we got the correct answer. On the test, if we set it up wrong, we would have got the wrong answer right away. We moved on and didn't realize we got it wrong, right? So this is one way of doing it. It's kind of long. It was a pain. Now, let's do this. Much easier, because x on this is what part in this triangle setup that we have. It's our altitude. So what we're using is that first formula. So we can do altitude is equal to part 1 times part 2. Now I'll probably just use initials from this point on. I wrote out the full words there the first time we did it. Part 1 times part 2. So the altitude on this figure is x. Part 1 is 1. Part 2 is 3. 1 times 3 is 3. We're done. Is that easy or is this easy? That's definitely easy. Again, the only catch there is you have two formulas that you have to know. But again, if you know these two formulas, it makes these problems 10 times easier. All right. Even on number two, we have 3 different variables to solve for. Could you imagine setting up 3 different sets of proportions to solve for that? I can guarantee you that there's other teachers here that will go through and do these proportions every single time. You have to do 3 different proportions, set that up, cross multiply, solve, take a square root. Crazy waste of time if you ask me. I've always preferred these because they're short and quick. All right. On here, number 2. Now the triangle is flipped. So if you want to, you might want to label it first. All right. So on here, I'm going to spend just a second to say, all right, here's my altitude. This one's the legs. I'm going to call that leg 1. This one's the legs. I'm going to call that leg 2. So then this is next to 1. So I'm going to call that part 1 and call this one part 2. Could I switch those around so this was leg 1 and part 1 and leg 2 and part 2? Yes. All right. But again, I just took a minute to label it just to help us out. Now let's solve. I want to get the altitude. So the altitude here is x. So for x, using my equation, which I already have it written over there, so I'm not going to write that one again. Part 1 times part 2. What are the 2 things I need to plug in? The 2 and the 5. And what's 2 times 5? 10. Can I do the square root of 10? No. So that's just going to stay square root of 10. That's my answer. We're already done with x. Move on. Now we're going to go to another one. Let's do, is that my phone? Yes. Can I come down in like 2 minutes? Okay. All right. But let me finish this problem, you guys first, and then I'll go. All right, where was I? So we did the altitude. Now we also have legs to solve for. So leg 1 over here is y. I'm going to solve for y next. All right. What 2 parts am I going to use to solve for y? The adjacent part. What's adjacent to the y? So the 2, right? Again, the adjacent part. So we're using these parts of the hypotenuse here. It's 2. What's the hypotenuse or the whole hypotenuse? 7. You have to add those 2 up. All right. So 2 times 7. We're at 14. Can I simplify that one at all? That says 14. I know that looks bad. Can you simplify it at all? Nope, it's not a perfect square, and there are no perfect squares that go into 14. So we're done. Move on to z. So now for z, same thing. Our equation here is the adjacent part times the whole. So what's adjacent to z? 5. The whole is still 7. 5 times 7 is 35. We're done. All right. We can't simplify that one either. So again, if you use these, they will save you a bunch of time. All right. Again, you just have to know them. You have to memorize them. All right. But again, it's the geometric mean of the 2 parts for the altitude, and the geometric mean of the adjacent part and the whole for the leg. for some of these other questions. Now, could they ask you to solve for something else besides, could I ask you to solve for something other than an altitude and a leg using those formulas? Yeah. You look at number 5, they already give you an altitude. They don't have legs. But for the legs, do you know what the hole is? No, there's another variable that's part of it. So we can't use either of those formulas to solve right away. For the altitude, though, we can still use the formula altitude equals part 1 times part 2. But now we know what the altitude is. We know what the first part is. We don't know what the second part is. So in order to solve this, we can get rid of the radical, square both sides. We're left with 4 equals 2x. And then divide off 2, and x is 2. All right. That's as far as I'm going. What I want you guys to try is page 7 only for your homework. All right. So page 7. So I know there's 2 pages on the back. Only do that first one, page 7. Don't worry about page 8. All right. That's what I want you to try this week. Any other questions? All right. And again, we'll practice more with the simplifying radicals on Monday. I wanted to at least start this section first so we had something to use for the simplifying radicals. It's hypotenuse. So the altitude that they have drawn in will always go from the right angle to the hypotenuse. So it's always going to split the side that's the hypotenuse. So you have the whole hypotenuse, and then you have the 2 parts of the hypotenuse. Any other questions?
What's up? What's up? You can talk about.